In this somewhat lengthy ICM tutorial, we're going to cover a lot of ground. So bear with me for about 28 minutes. We can always open a new ICM session, or you can clone one that you're already working on if you want to have two parallel things going on. But what I want to show you right now, first of all, is just to bring in a PDB entry. Now, obviously, you can bring in a lot of stuff from other resources. For the most part, we are only going to interact with the PDB with this tool for the purposes of this class. You've done this before. I'm just going to search for lopinavir, which is a drug, not a protein, but that gives us 7 hits. And of course, we can click the HTML link, and that'll open up the PDB file for the relevant molecule. We don't really care about that so much today. What we care about is bringing in the protein structure itself, and that's lopinavir. We'll take the first one. Reminding you that we have a workspace panel where we can turn off and on our molecular representations. We have a table of our results, and we have the graphics window. And we can manipulate those however we would like. We can go to the Windows menu to use a default layout, or we can say eliminate the terminal window if we want. Sometimes we don't use that very much. We can turn off the tables. And now this is probably the simplest representation we could hope for in ICM. We can bring back the terminal if we want. Reminding you that now that we have a molecule, we can use these new set of tools to display the light, the labels, the meshes, of course, the search. So there's our display. And if we click and, yes, we can zoom in and out using the different mouse buttons. I just want you to play with this to find out which mouse buttons are going to allow you to have which functionality. Right now, our principal tool is the rotation tool. If you look on your right side of the panel, you'll see that we have that rotation tool selected. We can turn off on objects with the radio buttons. So we can turn off everything by clicking the main object button. We can open that up by clicking the triangle. And we can turn on and off individual sub-objects. So we only have one protein open, 2q5k, but there's 6 or 7 molecule entities within that object. If we open up A, that's subunit A of this protein, we see the 1-letter code, and we can click and drag to highlight individual amino acids, and those appear as green crosses on the screen. Now I've drawn phosphates, I've drawn waters, I've drawn another phosphate, I've drawn so everything's represented here now that you could imagine wanting to have. And then usually where we begin is right-clicking on the molecule 2q5k and converting that to an ICM object. You can select all of these. Certainly want to replace the original to make things less complicated on our workspace panel. You can optimize the ligand tautomer or not, realizing that the tautomer that's in place is the one that the crystallographer has defined. So we'll change that. We'll optimize that now. And then you see that we're left with the same exact structure. Some new color coding has appeared that may or may not appear in your own, depending how your preferences are set. And I'm just going to march through and delete stuff now. Right-click on these phosphates, and I can shift-click or command-click or control-click to define how my selection for multiple objects works. I don't want to delete the ligand, obviously, so I'll select these phosphates all together. Clickety-click, click, click. Now I've got 3 phosphates selected. If I right-click them together, I can delete them all together. I just like to have a cleaner workspace, so I delete those extraneous objects. So we can turn off A and B. We see that, unlike other software tools, those are already presented as separate objects in ICM. Right now, the default is the ribbon. So if I turn off the ball and stick, that turns off the ligand, which was the only thing drawn as a ligand. If I turn off the ribbon, and on the ribbon, you'll see that the protein clicks in and out. And you can change some of the simple characteristics of the ribbon that way. I can draw the whole molecule 2q5k as a ball and stick representation, or I can draw it as just a ball and stick representation as opposed to a van der Waals structure, all space-filling models. I can draw individual units. And it looks like I still had some side chains drawn, so those are now not drawn. And if I turn off the ligand, I can select both of the protein objects and define the way that they're drawn only. So I've taken away the ribbon and got all the atoms selected for a ball and stick representation. I can select them again. Go back to the all atom representation. And now that those two are drawn together, the ball and stick and all atom, you can see that the all atom becomes, the space filling becomes translucent, which can be fun. Just to show you, you can also draw the wireframe, which is a slightly less chunky version of the ball and stick model. Again, for the purposes of most protein structured displays, drawing all the atoms is not usually the way to go. We usually select a subset of atoms that we'd like to display to make things as simple as possible for the observer. We can use a skin representation here tool in the displays to show a skin that represents the solvent accessible surface area. Imagine rolling a water molecule over the surface of your protein. You can turn that off as well. There are other ways of representing the surface, as I'll show you as we go along. We can adjust the color of our representation. Since we have our ribbon drawn, we'll choose any number of different options. We can choose by chain, which is how it's colored now. That didn't change anything, so we can go try something else like into C. So both chains are now represented as a rainbow from the end to the C termini of the protein. I turned off A so you could see that purple is the N terminus, one end of the protein. If we trace that through space, following the arrows, we see that we've gone through yellow now, orange to red. So those are the two termini of the protein. We'll bring back both again, and we can choose a custom color as well. I like blue. But now the whole molecule, both A and B chains, are colored blue. Sometimes that's confusing. It really depends on what you're trying to represent. You can also see that there's a fog button, which represents the depth queuing. How it's a mechanism for adding three-dimensionality to your representation. Again, it depends on what you'd like to show. So I'm going to change the B chain to gray. It's a fairly inoffensive set of colors there, but now I can see that the two monomers of the HIV protease dimer are represented and are symmetrically arranged. And I brought back my ligand, and I'll go to choose that by the color that by the atom type. That makes more sense. Our CPK representation, carbon, oxygen, and nitrogen colored differently. I can blow up my structure window here, zoom in and out. What else would we like to illustrate? Ah, yes, I can choose an object. I can click to select an object and center it. So now if I select on everything, it brings the whole molecule into focus as opposed to an individual amino acid or ligand molecule being selected. You can also play around in the display window with different labels that you can add, which for the most part are not going to be useful. Not going to come into play for our purposes. There's also ways to add your own labels. You can create your own label doesn't have anything to do with the PDB file, and you can enter something if you want and adjust the color of it and the font size, etc. It's a little hard to move that around, but again, that's not really going to play such an important role in our work today. I'm just trying to get rid of that. There we go. So you can add labels should you wish. Let's play around with the selection options. So we can open both of those amino acid sequence for both chains and highlight individual amino acids. I'm showing you here that the green underlining in this case indicates a type of secondary structure, beta strands. So you can see that there's more information in the sequence window than you might have thought. You also get some structural shorthand information. You can select individual atoms. Here's some various selection tools. I'd like you to play around with those yourself. A useful tool might be to define your selection properties by amino acid type. So we can select all the alanines. You see all the alanines appear, the glutamic acids appear, etc. If we move out of the way and select our histidines, we see that there are 2 histidines, one in each monomer. Those are highlighted in the sequence area as well. That can be very, very convenient. We can select by category, amino acids or heteroatoms. We've gotten rid of all of our heteroatoms, the phosphates, etc. So that we can play with our selection properties as much as you'd like. I encourage you to play. All right. Let's remember that the active site amino acids in HIV protease are this DTG starting at amino acid 25. So I've drawn those, and you can see those all drawn there, including the backbone. So something I'm going to try to show you is that you can adjust which amino acids that you'd like to, what atoms in the amino acids you'd like to display. What we're going for here, I'm changing the atom color to the standard. What we're going for is to get rid of all of the backbone so that it appears the side chains are more or less emerging from the cartoon ribbon that we have drawn. Now, of course, if we go to chain B, we'll see that there's a symmetrically arranged DTG triplet on the B chain as well. We can color those just the same way. Notice our ribbon changed colors. We can go back and change that later. I'll show you how. So that's interesting. It shows us how the protein, the details of how critical interactions between amino acid side chains and the ligand are forming. And I've highlighted those atoms again, and I'm turning off the ribbon. I'll worry. You can play with the color of the ribbon directly, but let's not worry about that. I've turned off the ribbon for now. You can see that the selections are there whether or not you're displaying your molecule, and you can unselect those atoms as you go. So I'd like to show you how to unselect different atoms. There's our ribbon back again. The easiest thing to do I'm recoloring my ribbons here. You can see that you can recolor the ribbons individually as opposed to changing the entire molecule. So that can be convenient. So now I've gone back to a blue and a gray, and I've chosen on the right hand side an individual atom selection tool. So now I'm just going through the backbone, getting rid of atoms. You'll see how I undisplay them in just a moment. So I'm just choosing which atoms, atom by atom, to see which ones I want to eliminate. Just my goal here is simply to leave the amino acid side chains present, and you'll see that it's going to look much cleaner. So I'm selecting several things here. We'll continue selecting. And since they're already drawn, if I select the ball and stick button, they disappear. And you can see that leaves some protons floating in space. We'll go pick those up as we go. But now you can see there's fewer backbone atoms now. Some you might want to avoid getting rid of if your amino acid doesn't come directly from the cartoon ribbon structure. So the goal here is to clean the structure up to make the representation as easy to interpret as possible. So bit by bit, I'm chipping away at the ball and stick representations that are not doing what I want. So there's more backbone. That's just a glycine. So in fact, The glycine has no side chain, so I'm just going to delete the glycine entirely. And what we'll see is that the really interesting feature of the HIV protease active site are those two aspartic acids. You see the two red oxygen atoms there on each side of the ligand's hydroxyl. Those are the carboxylic acids. So I'm getting rid of this threonine here on each side. And you can see I've still got a few protons floating in space. It looks very strange. But I can just turn off protons. If you notice that up in the top left, there's a proton button. There's a few different proton options that we can get rid of, or that we can affect. Still one or two atoms left that I want to get rid of. That must have been a peptide bond proton. So, okay, we're almost there. Oh, still some backbone stuff there. You see a peptide carbonyl hanging out in space. Let me get that guy. Gone, gone. I'll just get rid of this whole threonine. So we brought him in, but we can take him out atom by atom. Now what we see is that these aspartic acids appear to emerge directly from the cartoon backbone. That's not physically realistic, but the cartoon isn't physically realistic. And so the point here is to draw the simplest representation that gives the most interesting and salient features. And what I've done then is show you that these two aspartic acids on A and B are aimed directly at a particular piece of chemical functionality on the ligand. Now I can select the ligand and add the space filling rendering to the ball and stick, and you see when you do both of those, it renders it as a translucent spheres, and that's useful. It gives you a sense of the bulk of the ligand and how tightly it's packed into the active site of the protease. I'll select it all, and let's go to meshes now. So all the protein, not the ligand, is selected, and we can choose a series of options, but we'll choose electrostatic. We can choose occlusion is a lighting feature, and when we click the skin button, it'll take a moment to calculate. You'll see that the red stop sign will appear at the bottom left, telling us that the computer is thinking. It's a complicated electrostatic potential. Surface is a computationally expensive procedure, and now you see the overall electrostatics of the molecule, red, highly negatively, electrostatically negative all around this molecule with a couple of blue sites. That can be very important for understanding the activity of your enzyme, not so much for HIV protease, but it is very beautiful, fascinating. We'll select that again. We can, as compared to the ball and stick representation, just giving you a sense of the difference between those two. Imagine rolling a water molecule over the surface of your protein. It can't penetrate into every crevice, so you have this sort of smoothed out surface representation. We can go back to the meshes and just color it as a plain solid. And we can change the, oh, actually, oops, I had the ligand selected there. Let me turn up, that's okay, I want that. I was trying to affect the protein's skin. So see, I made a mistake there, so we can get rid of that guy. We don't care about a molecular surface for the ligand at this point. So get our proteins only back up there, compute the plain solid, much swifter calculation, and there you see a plain white solid molecular surface rendering. Okay, I'm just cleaning up a little bit here. Now we only have one skin. We'll get rid of it, play around. I'll do a skin for one monomer. You see that? The A subunit. You can play with your color options. You can link it to the color of the ribbon diagram, which we can no longer see. But for now, we'll come back to that. So let's also do the same with B. again coupled to the ribbon color. What I'd like to see though is the ribbon structure underneath. So I'd like to create a translucent mesh, and that's easy to do. We click on, let's see, oh yeah, right, so we can turn it off and on and off there, but if we right click on the radio button itself, then that gives us the option of creating a smooth transparent surface area. And we see that for both surfaces. Now, the gray ribbons are a little bit challenging to see here, so we can play with that as well. Again, reminding you that the goal here is to create the most easily interpreted structure. So if you feel like any element of your structure is getting in your way, consider getting rid of it. What we're trying to show here is the active site of the HIV protease. So I'm just changing the structure, the color of the ribbon. I've selected B only, and I'm changing the color of the ribbon. I'm making it progressively darker in the hopes that our surface rendering will become easier to interpret. I'll go to my color wheel, 256 million colors to choose from. We're getting closer. It's a little bit easier to see now. Ghost protein, appropriate for our Halloween coming up tomorrow. Not dark enough. Make it darker. There you go. We're starting to see, especially as we rotate through different shaded regions, we can see that it gets darker and darker. We can bring back A now. And that's a nice representation of HIV protease bound to leponavir. Reminding you of your clipping tools. We can clip from the front. Again, depending on exactly what your objectives are for your representation. We can go back to our rotation tool. I've turned off the skins here, the mesh representations of the solvent accessible surface area, and we're back to simply the ribbon diagram. And you can see how much darker the B subunit, the B monomers ribbon is now. And I'm just zooming in on the active site, showing you some hydrogen bonds. So here we see again next to the ribbons, we can turn on and off hydrogen bonds. Those will be color coded and size coded for the distance between the two hydrogen bond donor and acceptor. That can be useful, showing you which atoms are directly engaged in hydrogen bonds. We can add that for the whole molecule, but only if you have the all atom representation drawn. So I try as I might, if it's just ribbon structure drawn, I won't see any hydrogen bonds. Now we can make a movie. There's the movie picture, the movie icon. We'll give the movie a name and a location. Remember to give names and locations that are meaningful to you and easy to recall and find again. I'll put mine in 30517, and I'll call it test ICM. It hasn't begun the movie yet until you click the red record button. And now it's recording a movie. At this point, you want to decide and define exactly what you expect to show in your movie. So we've zoomed in on the active site. Very close up look at the two aspartic acids engaging with the ligand molecule. We'll zoom back out. We'll do a rotation. I'm manually doing this rotation. There's a couple of ways to program the rotation, which we won't go into now, but I encourage you to play. So we've done a full rotation. We'll back out a little bit farther, showcase this molecule a little bit more, and do another rotation. bring our skins back. So now finally we see the full surface representation, and I'll pause it, stop it, and see that the command window has given us this output of test ICM movie being written out to the proper location. And I can bring it up. I'll go search my Finder for that. And here's the movie, 20-second movie. We'll play it, it zooms in, it zooms out, it spins around. Notice how much of the protein is cropped. So you want to think about, again, what kind of representation you want to show for your protein. We zoom out, we do another rotation, we bring in our surfaces, and we're done. All right, save your work. In fact, I've waited too long, 20 minutes, to save this work. You want to save as you go. Get in the habit of that and you will cry less. Let's play with some of the other options here. On our light menu, you can see what happens if we adjust the shine or the intensity of the ambient light, the diffuseness of the light source, specular reflections of the light source, transparency of the object can be very relevant to you. There's a number of ways of adjusting transparency, the brightness of the light, the position of the lighting. All of these things are under your control. You have fine-grained control over how you represent your molecule. Selection tools, you have a variety of selection tools. You can select directly from the image and you'll see that you can affect the way those are rendered on the screen, your selection. Just to show you those hydrogen bonds, remember hydrogen bonds are still selected, so if I draw the all atom representation of the B subunit, you see all of those hydrogen bonds. And if I recenter it and switch myself away from z-axis rotation back to three-dimensional rotation, we'll see that all of those hydrogen bonds in the beta sheet network are apparent now. Let's color code those by atom again and zoom in to the beta strand. And note that some are closer than others, so they have a greater strength. Blue fat balls are the strongest hydrogen bonds, green medium-sized, red longest, weakest hydrogen bond. All right, turned off the ribbon, that's nice, less confusing. If we open the sequence, let's turn off everything, and then remember that the green underline tells us which amino acids are involved in beta sheets. So I've selected 2 beta strands that are connected by a beta hairpin, and I'll recenter those, and you see that that's one small stretch of beta sheet, 2 beta strands linking to form a small sheet, and the hydrogen bonds are formed between peptide carbonyls and peptide amide groups on the neighboring strand. That's all for this demonstration. There are plenty more functions for you to engage with. I strongly urge you to play around and have fun. As you have fun, choose your own molecule, your own protein, your favorite protein, for which you'll do the sort of representations that I drew and more, and present those as a movie at the end of the class. Enjoy.